Hi everyone, let's get started. In the past couple lectures, we've been talking about training RL and imitation learning systems that can do multiple different tasks. And we first looked at this from the lens of multitask imitation and reinforcement learning, where you condition a policy or a queue function, not just on the state, but also on some sort of descriptor of the task, or where there are also scenarios in the goal condition setting where that descriptor could actually be a state itself, like a goal state that you're trying to reach. And then more recently, we were talking about meta reinforcement learning, where you could think of that instead of kind of conditioning on a description of the task you want to do, you actually need to figure out from a few examples and a little bit of experience with rewards what the task is. And you're trying to train this sort of like few-shot policy that can adapt with a small amount of experience. Now today, we'll be kind of building on some of these concepts and trying to not just train a policy to do multiple tasks, but to actually string together behaviors for multiple tasks into a longer horizon task. So this is where we're going to be talking about where hierarchy might be helpful for solving long horizon tasks. And then we'll be talking about some of the key design choices behind hierarchical imitation and reinforcement learning methods, including how to represent skills and goals, when to move on from one goal or task to another, and the supervision for the different levels of the hierarchy. And then lastly, we'll go through a couple examples of like what these systems could actually look like, because there are like a variety of different ways that you could design these sort of hierarchical systems. So the tasks that we'll be talking about today are long horizon tasks. And by long horizon tasks, I mean tasks that take a while to complete and might consist of a number of different subtasks or a number of different steps that you need to take in some sort of sequence or order in order to complete it successfully. So this could be something like cooking a meal. It could be for like a robot system, for an LLM agent, it could be trying to fix a bug that's causing a neural network training loss to explode. For an autonomous vehicle, it could be driving to Yosemite. For a different sort of LLM, it could be giving feedback on a long report. And for these tasks, you can think about how there are oftentimes different steps that you need to complete. Some of those steps might be interdependent on one another, where it makes sense to do one before the other. And other tasks might be something where they're less interdependent and it's actually okay to do those in parallel. These are really hard problems for AI systems to solve in general. And the reason for that is, there's kind of a number of reasons for that. So the first is that when you are doing a task that takes a long time, you're visiting a large number of states along the way to get there. And every new state that you visit, you need to be able to make decisions for. So you basically just have a much broader distribution that your policy needs to be successful on. There's also a lot of different opportunities to make mistakes. And if you make a mistake, you need to be able to recover from that mistake, if it's something that you can actually recover from. And separate from mistakes, there's also just opportunities to get stuck. For example, if there's kind of one kind of mistake that might, for example, not lead you to actually make progress on the task. And if you're not making progress, then you'll actually just end up in the same state again. And you'll keep on making that same mistake over and over again and essentially just get stuck at performing the task. And these kinds of mistakes are kind of particularly gnarly because they, when you end up in the same state again, your policy will keep on kind of deterministically staying in that state and never making forward progress towards the goal. And then what's the main idea behind hierarchy? So we've talked about multitask policies where you have some, actually let me draw this further to the right. We have some policy that takes as input some state, maybe the state at some time step, and it also takes as input some task or some goal. I'm going to write this as G for now because this task or goal could take a number of different forms. And this is passed into your policy to produce actions that are trying to address that particular goal. the idea for trying to solve long horizon tasks is if we have a policy that can do a number of different things, then we could try to break up a bigger task into different subtasks, and then use one policy to actually tell this policy what task it should be doing at any given point in time. So, for example, you could have another policy here that's actually outputting the goals to be doing. And this policy should also have information about the state as input, so that it knows where it is and what goal makes sense for the next, for the agent to do. And then optionally, this is often called like a low-level policy, or we'll use PyLL to refer to this is kind of the low-level policy. This is doing shorter tasks. And we can refer to this as a high-level policy that's outputting goals for the low-level policy to accomplish. And this policy, it can have a task. You may also, sorry, I wrote this as low-level. This should be high-level. If you want your policy to be able to do multiple long horizon tasks, then this high-level policy could also have some sort of task descriptor as input as well, or some sort of goal as input. And so we, for example, could have goal high level as input to this policy if you want to be completing not just one long horizon task, but multiple long horizon tasks. Like not just driving to Yosemite, but also being able to drive to the Grand Canyon or LA or Seattle or something like that. And the kind of crux underlying this idea is that if we can break up a really long task into smaller parts, then we might be able to better address the problem. And say, for example, your long horizon task is to bake a cheesecake. This is a really, really hard problem, and if you just tried to train a policy, like a robot policy, to output motor commands for doing this task, it's really hard to figure out like what you should be doing at any given point in time. But if you're just starting out, you can think about, okay, what's the first step for accomplishing this? Maybe you need to buy ingredients. Okay, then what's the first step of buying ingredients? Well, maybe you need to go to the store. And how do you get to the store? Well, maybe you need to walk to the door. To walk to the door, you might take a step. How do you take a step? You might contract a muscle. And so you can basically break down a bigger task into a much smaller task. And these smaller tasks are a lot easier to train systems to do. And if you can train systems to do the smaller tasks, then you could try to compose them with like a higher level policy to be able to accomplish that more challenging task. So what we can do is for the bake a cheesecake task, we could pass this with a state or observation into a high level policy, which is going to predict an intermediate step, like for example, go to the store or go to the door. And then that intermediate step, along with the state or observation, will be passed to the low-level policy to predict an action. Now, a couple notes here. So one note is that this low-level policy, this needs to be acting at the original kind of frequency. So if you're controlling a robot, maybe this is operating at like 20 hertz. If you're controlling a language model, then this is going to be outputting like word by word. Whereas the high-level policy, it could actually predict goals for the low-level policy at a coarser timescale. And so, for example, it could be outputting goals after you've completed a paragraph for a language model, or after you've completed that, like going to the store, for example. It could then give a new goal for the low-level policy to perform. And so we have a high-level policy that predicts intermediate goals, and then the low-level policy tries to accomplish those intermediate goals by predicting actions. Typically, the low-level policy is operating at a higher frequency than the high-level policy. And I should note that I'll refer to these as kind of goals or subtasks. There's a number of other names for these as well, like skills or options. You could also think about these as high-level actions. So these are actions, but for a different policy that's operating at a higher level of abstraction than the original policy. And then the other thing here is that this is kind of like a two-level hierarchy, but you could also imagine having more than two levels of hierarchy as well. And for example, the baking a cheesecake, you could have maybe one level of hierarchy could be like things like go to the store, like buy the things, bring them back. And a different level of hierarchy might actually be controlling like the motors on a robot in order to accomplish those tasks. And then once we have this sort of hierarchical policy, how do we actually like roll it out if we can do these things? So specifically, if we're at like, say, we'll start at t equals 1, then the first step is to predict, or another kind of way to think about kind of predicting a goal is planning. Like we're trying to think forward, what is the next step that we should do? So we could try to plan a goal, and this will be by sampling from our high-level policy based off of the current state and optionally some sort of high-level goal. And then we'll be repeatedly sampling from our low-level policy. And so we could repeat, first sample an action from the low-level policy using this goal as input. So sample A from pi low-level with the state and this goal, the goal from the high level as input. And then we'll actually execute that action and get the next state. So basically, at that point, we'll then kind of, t will now become t plus 1, and we'll observe st, then again with the same goal as before, but the new state will then be sampling a new action, repeating this process. And then at some point after we have, and we'll talk a little bit about how we decide when to get a new goal, but when we have decided that we're either done with the goal or enough time has passed, then we'll move back to step 1 to replan a new goal based off of the latest state. Yeah, so the question is, let's walk through this and then I'll get to your question in a minute. So is there some initial state or observation, plan a new goal? Until a new goal is selected, we're going to execute a predicted action according to our low-level policy based off of that predicted goal, and then we'll observe a new observation. Now, why might hierarchy help? Which I think was kind of getting at your question. There's a couple reasons for this. So the first is that typically we're going to be training this low-level policy to reach goals and this high-level policy to maximize rewards or reach some high-level goals. And this means that the objective for this policy is different than the overall objective of completing the long horizon task. And so this is actually getting different supervision, and this intermediate supervision signal for how to complete intermediate goals or tasks can be useful for guiding the policy towards completing the long horizon task. So you can think about it potentially, it kind of depends on the setup, but you can think about it as a way to leverage intermediate supervision. Now, you could always have intermediate supervision when training a big flat policy as well, where you give it shaped rewards and you give it rewards for completing individual subtasks. But compared to that, the other difference here is that this low-level multitask policy is going to be able to more explicitly share knowledge across the different subtasks. Because, for example, it has this goal as input, it's kind of targeting a particular subtask. And if two subtasks are quite similar to one another, then this policy will be able to kind of share data across those tasks in order to more efficiently learn, compared to if you were just to try to train a single policy across the long horizon task. In reinforcement learning specifically, you can also think about benefits in terms of exploration. And in particular, when this high-level policy is proposing kind of goals to reach, that's structuring the exploration process to encourage it to explore not just in the original action space, but also in this higher level goal space. And lastly, there can also be sometimes practical benefits as well. So for example, if you're thinking about this task of making a cheesecake, for example, you might need to be reasoning through the steps for how to do that. And if you have a single policy, then you need to reason through those steps every single time step with that flat policy. So if your robot is operating at 20 hertz, for example, you're going to be reasoning through, like, what is the next thing I should be doing and the way to get there with my action at every single time step, where here we can kind of run this reasoning computation at a lower frequency than the low-level policy. So that can be kind of a practical benefit in terms of compute costs. Yeah, so the question is, like, can we elaborate on the first point and how the supervision for the low-level policy is different for the high-level policy? So the high-level policy its goal is to complete the long horizon task. So its goal is to, like, bake the cheesecake, and it gets rewards when the cheesecake is baked. The low-level policy, it gets rewards for completing intermediate subtasks. And so when it, for example, finds the ingredients, preheats the oven, that sort of thing, it's getting rewards for completing those tasks. And that sort of intermediate supervision guides it towards completing the long horizon task. Yeah, so the question is, like, what if you need to be doing multiple tasks at once? So in that case, unless your low-level agent can, like, has, like, I don't know, 10 arms or something, or can output things in parallel, you do need to pick some order for that. Now, the goal of the high-level policy is to figure out whether that order matters or not. And so if it figures out that the order is really important, then it will get rewards. It'll be better able to predict those goals. If it predicts the correct order, in other circumstances, if the order doesn't matter, then it should be able to learn that and figure out that it doesn't really matter, and it'll just pick one arbitrarily. Now, there's also a question, like, of whether or not we, like, actually need multiple policies in order to get some of these benefits. And on the last slide, we talked about kind of the benefits of what you might get with a hierarchical approach versus just what's called a flat policy with no hierarchy, which is kind of the typical pass in the long horizon task and the state and predict the action. There's actually also an intermediate approach that you can take as well that actually retains a lot of the benefits of hierarchy, and actually in some ways has a lot of the same design choices, which is something that's a little bit like chain of thought in language models, if you're familiar with that, which is that if you have some long horizon task, you could have the policy first, like, reason through what goal or what subtask it should be completing, and then predict the low-level action. So this is kind of combining these two policies into one, but now you're just kind of predicting them in sequence. You're first predicting the goal and then the action. This sort of approach can actually retain a fair number of the benefits, so you can benefit from the same sort of intermediate supervision. It also might have some practical downsides, so this doesn't have the benefits of the kind of practical computational benefits of separating them into two, because then you still have to run this at the full frequency. There isn't, like, entirely a conclusion yet empirically on whether this is like just as good as a hierarchical approach. And you could imagine that, like, there might be benefits in terms of, like, sharing some knowledge with low-level policies versus with a combined approach. So this is, like, an open area of research on whether or not you could just do this. And the only, like, really conclusive downside would be the kind of the computational upside of having reasoning at a lower frequency than taking actions for the first one. So the question is, why is having intermediate supervision helpful? There's a couple reasons. So if you're in a reinforcement learning setting and your goal is to make a cheesecake and you only get rewards when the cheesecake is baked versus not, then those rewards are going to be really sparse and not actually allow you to progress. The second is that even if you, say you're in an imitation learning setting and you, you're just predicting actions, like imitating actions for making a cheesecake, then, sometimes, like, if the policy isn't explicitly thinking about what part of that task it might be doing, it might kind of oscillate between different subtasks, especially if it doesn't have a history of past observations. So there's also even benefits in imitation learning settings as well. So now let's dive into some of the design choices. This will kind of also start to answer some of the questions that have come up as well. So the first is that we've kind of abstractly been talking about these different goals. And we need to think about how to actually represent those different goals. And I actually want to start with this as an exercise for you all to think about what different representations might make sense for different problems. And so I'll give you a few different example problems, and then the goal for you is just kind of think through for that particular problem, what would be kind of sensible intermediate steps for the agent, and how would you actually represent those different intermediate steps? So the first task is a robot that wants to learn how to cook Italian dishes like focaccia. What would kind of the intermediate steps for those cooking tasks look like if it needs to kind of control its motors to complete that task, and the representation for that. The second one is maybe you're developing an autonomous driving bike, and you want it to break down kind of navigation and biking to various locations on campus. The third is a language model that is drafting legal briefs, which is also a rather complex and involved process. And then the last is maybe a web agent that needs to plan and book 1-week vacations for users. So I'll give you a couple minutes to pick one of these, discuss with your neighbor what intermediate goals would look like, and then we'll come back and discuss. Does anyone want to share what they discussed? Cool, yeah. So for number 2, one way that you could address it is the different intermediate goals could be kind of like waypoints towards that particular goal location that you want to reach. And then the representation for that could be GPS coordinates, and the reward for the low-level policy would be like, how close are you to those GPS coordinates? So yeah, something like that makes sense. Anyone else want to share? Either for that problem or a different problem? Yeah, cool. So for the fourth one, there's a few different ways you could think about it. You could think about it as like intermediate goals are like booking day 1, booking day 2, booking day 3, or you could have a more course-defined approach where you're like booking travel, booking, I don't know, hotels or whatever, and then specific activities. One other part of this that I would imagine you need to do is like kind of just generally figuring out what does the user want from their vacation. And so doing kind of high-level research first. And that could be kind of also an intermediate goal as part of completing the task. Did anyone pick 1 or 3? Okay, so the intermediate goals are things like opening the cabinet, beating the eggs, and then, sorry, the representation for those goals? Okay, didn't quite get to that. So, but one thing is, so a few things that you could do for the representation for that is it could just be a natural language. So it could be like literally like the string beat the eggs or open the cabinet. If, for example, if you're cooking something where you want to look in a particular way, you could even have an image as an intermediate goal representation as well, saying like, I want the bread to look like this, or yeah, that sort of thing. So you could imagine like multimodal goal representations as well. So one of the things that I kind of wanted to convey with this exercise is that oftentimes the goal representation that you might pick is likely depends on the particular domain or the particular problem. For example, like for biking, it might be something like GPS coordinates, whereas for cooking, it might be language. For booking a vacation, it might also be in language. There might also be images involved and so forth. And in terms of what these goal representations might look like, oftentimes you'll want it to be if you're kind of developing something for many different subtasks, you want it to be fairly expressive. Like if you're trying to cook lots of different meals, like natural language is something that's like quite expressive and can describe a number of different low-level behaviors. Ideally, it also has some structure. And so, for example, if your different goals are just like do subtask 1, do subtask 2, it's going to be kind of hard for your low-level policy to figure out how those relate to one another. Whereas if you have something like GPS coordinates, then 2 GPS coordinates that are very close to each other are going to have similar actions. And that sort of structure will make the learning problem a lot easier for the low-level policy. And then the third thing is also picking an appropriate level of abstraction. So for the kind of the biking task, for example, you can have like a level of abstraction that's like potentially too low level. So you could have something that's like kind of pedal, I don't know, like current, like exact velocity for the next second. You could also have something too high level, which is like go to the quad or something, which might not be particularly helpful in terms of breaking the problem down into smaller steps. And choosing the right level of abstraction is often somewhat tricky. And can also be domain dependent depending on the particular kind of details of the problem and the application area. So the question is, should we also abstract the state space for each layer? This depends on like whether or not you have access to that, like that sort of like abstraction layer. Let's see, oftentimes, even for the high level policy, it's helpful for it to have all of the information about the current state in order to make kind of even high level goal predictions. But yeah, there are kind of some things that you can do. For example, you could, for example, like ask a language model to summarize kind of the high level information about a state and have a high level policy use that information. But generally in practice, you'll often use like the same low level, like the full state information. You don't lose too much from doing that as well. Now let's talk a little bit about the supervision for each level. And for this, I think it's helpful to kind of go through, to kind of consider an example. So let's consider an example where you're making pasta. And I chose this to be a slightly simpler long horizon task. And you could imagine there being a few steps involved for doing this. And we can kind of abstractly think about the state space for this task and reaching different intermediate steps for this. So for example, maybe, let's say that this is your kind of initial state distribution. And the steps for making pasta is that you'll need to like get out a pot and pasta, so some ingredients. You'll need to boil the water. And you'll also need to pour the pasta into the boiling water. Maybe there's also a straining step, but maybe we can skip that for now. And we could think about the like imagine kind of the set of states that where you have like, for example, you have taken out a pot. So like find a pot. Before actually like putting any water into it. You could have some states where you've now have kind of boiled the water. Another set of states where you have like found the pasta. And then some other states where like the pasta is cooked. And let's say that if we have kind of our low-level policy, it's going to be trying to figure out, like, how do I take actions to reach these kinds of states? And then the high-level policy is trying to predict which, like, if I'm in a given state, what command should I use to tell the low-level policy what to do? And generally, as we've talked about a bit before, for the low-level policy, it's going to be getting rewards that are based off of the low-level tasks. And the goal of something like this would be something where, you're kind of moving towards finding a pot. Maybe maybe then you kind of try to boil the water, then you try to find the pasta, and then you try to cook the pasta. Now, one thing that we talked about a little bit before is, so this is actually deviating from this example a little bit, we'll come back to it, is we could also just train the high-level policy and the low-level policy end-to-end without any intermediate goal representation. And so we would just, for example, we'd have some sort of kind of latent goal representation that's just the activations of the neural network. And we could kind of train all of these just for the high-level task and the rewards of completing the task. Now, one important thing that is good to know about kind of this sort of supervision is that if you do that, that's basically just a flat policy with a different, like a particular architecture that has some sort of like kind of activations when you feed in the observation twice. You kind of just think about that as basically a single neural network architecture that's basically the same as a flat policy. And the reason why it's important to recognize this is that when designing these kinds of systems, it's important to think about where the benefits are coming from, whether it's coming from additional supervision, whether it's coming from structured exploration. And if you don't think carefully about this, you can end up in a situation where kind of intuitively, if you haven't thought about it, it's like, oh, like ideally my high-level policy will do this, my low-level policy will do this, without actually seeing benefits compared to just kind of naively training things with a single policy. This actually also, if for those of you that are doing research, is also just generally something that's good to do in any kind of research, because you never really know if the systems that you're developing or the methods that you're developing are going to improve over some existing kind of state-of-the-art method. And if you're very honest with yourself around what might go wrong and why you might not actually see benefits from your new idea, then you can think more critically about what sorts of things will actually improve the final results. Cool. So supervising each level. So we have the low-level policy, and the low-level policy will be trained to accomplish the goal, not the original task. And so when you're passing in the string of like find pot, it's going to be getting a reward that is trying to kind of maximize reward for getting to the states where you have found the pot. And the high-level policy, its goal is to predict these subtasks so that you end up in the final state of the pasta being cooked. So this is kind of trying to accomplish the original goal. Now, there's a couple things that can be a little bit tricky about this. So say that you're training these separately, and say that you've kind of trained, you could, for example, think about training a policy to find the pot, and maybe you've like gotten to a good policy that's like really good at kind of finding the pot and getting to the state really reliably. And then say, for example, when you have, and then maybe, for example, when you train the policy for finding the pasta, if you did this, if you weren't exactly careful with how you did this, maybe you would think about, okay, maybe I could actually just start from this state and also try to find the pasta from this state over here. And that's not taking into account that actually when it's finding the pasta, according to like the high-level policy, if the high-level policy actually wanted it to find the pasta after boiling the water, when you're at the stove, then when you actually try to string together this low-level policy with the low-level policy for these two, it'll actually then struggle to transition from going to the stove over to finding where the pasta is. And this is basically like a mismatch when you're kind of training these modular systems. You need and you're training them completely independently. You might not actually get a system that works effectively if they're not actually at some point connected together and trained such that this skill is starting from states that where the high-level policy will actually start commanding that task. And so essentially, when you're training the low-level policy, you have your low-level policy actions given states and goals. You want this policy to work for the set of states where the high-level policy is going to command this particular goal. Another way to think about this is that, and I guess the other thing here is also you want it to be able to pick the goals that actually the high-level policy would predict. So for different distributions of goals and different distributions of states, ideally that low-level policy would work for whatever states and goals the high-level policy will output. Now, if we haven't actually learned a high-level policy yet, this leads to a bit of a kind of puts things in a bit of a tricky situation. And likewise, for the high-level policy, if we assume that our low-level policy is really great, then we might not realize that that it actually has some deficiencies and that we need to, for example, continue to command something in certain states until you've actually reached a state that a different skill can operate in. Yeah, so if the low-level policy works from particular sequences of states, then the high-level policy can learn that it should kind of walk the low-level policy through those states. So you don't necessarily need your low-level policy to work from every state. It just needs to work for the state goal combinations that the high-level policy is going to command. Now, you might have a situation where, say that your low-level policy kind of knows how to do kind of something like this. So it knows how to go from here to here. It knows how to go from here to here, and maybe knows how to go from here to here. Like with some boiled water, then you might have some sort of gap where to actually find the pasta, you need to kind of go back to these states And if you don't have a command, or some way to get from here to here, then you're going to basically have a gap in the states that you're visited, and the high level policy will struggle, to actually get to this state here. And so basically one way to think about it is you need to make sure that there's like at least some overlap in the states from one skill to the next. And ideally that overlap is has some buffer, because if, for example, when you're trying to find the pasta, it only works like if you're like standing exactly in front of the boiled water and not if you're like a little bit to the right, then if your policy ends up deciding to boil the water standing a little bit to the right of it, then you'll get a brittle final result where it will kind of struggle in that case. So the way to think about that is that, I guess one way to think about it is that if this low level policy only works from like this part of the states where the water is being boiled and the high level policy gets you here, or the previous low level policy gets you here, then you're going to have a little bit of a gap between here and here. And that sort of gap can lead to brittle performance on the full long horizon task. Yeah, so the question is, does it have to be a fixed sequence, and can you like learn if one sequence is more efficient than another? And yeah, so absolutely, the high level policy can actually decide which sequence it wants to do, and that sequence might depend on what's the most efficient. It might also depend on where the low level policy is most successful. And so, and one of the reasons why I wanted to pick this example is actually these two steps can be done in any order, and the high level policy could decide that when you're here, it actually wants to command you to go here. As long as the low level policy knows how to find the pasta from these states, then that might be more efficient overall. There's also worlds where maybe this would be more efficient because maybe while you're boiling the water, you're just waiting and you can find the pasta in the meantime. And so I guess there's also a pouring water and turning on the stove and so forth. So there's more steps involved. But yeah, the high level policy can decide which order it wants to take. Okay. So generally the way to address this is that you can first train them potentially completely separately. But it's important for at least one policy to be adapted to the other. And ideally, even both could be kind of jointly adapted with each other to optimize reward, or optimize some kind of complete objective. Cool. One other side note, I guess, that I think is worth mentioning is that even for problems that are not like traditionally LLM problems, LLMs are actually often pretty good at some of the higher level reasoning that you might want to do. And so, for example, if you know that you want to cook pasta, if you ask a language model what are the steps involved with that, oftentimes they can actually give you that. And so this is one way where you can actually kind of train the high-level policy completely separately from the low-level policy, and then potentially fine-tune them, because the language model, for example, might not know that kind of which order the low-level policy is best suited for, or other things about the capabilities of the low-level policy. And so that sort of adaptation process, even though language models are pretty good at this, that sort of adaptation process is really important. Also, if you ask, if like a robot is in front of a coffee machine and you ask the robot to get some coffee for you, if the language model doesn't actually pay attention to that image, it might tell the robot like, oh, can you like go out and buy coffee, like at Starbucks or something? And the robot might not have that sort of affordance, that sort of ability to do that. And so kind of adapting these two together. That's another example where adapting these two high-level and low-level policies together is quite important. Okay. The last key design choice that we haven't talked about yet is when to move from one task to another. So we outlined this process here, and we didn't really spend that much time thinking about like how long do you repeat sampling from your low-level policy to accomplish a goal. And essentially, it's like how often do we requery a new goal from the high-level policy to pass to the low-level policy? So basically, yeah, this step right here. So there's two natural options for this. The first natural option is to requery the high-level policy whenever the low-level policy has completed the goal. So when it has boiled the water, that's when you tell it to go find the pasta, for example. And the way that this would look like is, at this point, your low-level policy not only needs to predict action, but it also needs to predict whether or not it successfully completed the task. And this could be either with some sort of binary indicator or through some sort of progress indicator. You could think about this done, not done sort of as a success classifier for the task. And then the other option that's a bit simpler, but maybe less elegant in some ways, is just to simply requery the high-level policy after some fixed number of time steps. So maybe you query the low-level policy like at 50 hertz, and you query the high-level policy once every second. So then you would be querying the high-level policy after 50 time steps. So there's pros and cons of each of these two options. For the first case, where we're doing something after we've completed a goal, this is actually ideal. Like, if you're to do this well, this should be the most compute efficient, because you're waiting for the low-level policy, and you don't need to kind of rethink how you're doing the task while the low-level policy is executing. There's a couple things that are tricky about this, though. The first is that it can actually be hard to estimate when you're done with a task. This is actually it's definitely not trivial to do this. And the second is that you actually need to account for mistakes that require actually redoing some past goal. So for example, if you are trying to, organize some things on a table, you go grab something and then you accidentally drop it on the ground. Your sub-goal should no longer be put that object on the table, and instead it should be to pick it up off the ground. And this means that actually you need to now estimate not just when you're done, but also whether or not you've actually kind of exited the states in which that subtask makes sense. Then kind of going back to the fixed number of time steps, this is less ideal because we're going to be probably wasting some compute, and there's going to be a trade-off between spending more compute thinking through what the next goal should be, versus if this n is too long, then you're going to be delayed in transitioning to the new goal, where your agent will be, for example, maybe it's kind of found the pot, it's taken out the pot, and it's waiting for a new goal. It might just be, if n is too long, it's just going to be sitting there with the pot, because it's okay, I found the pot, and that's the goal that it's getting. And there'll be some delay before it then moves on to actually finding the pasta or pouring water into the pot. So there's this kind of trade-off between how long n should be. Generally, because you don't want these really long delays, you'll pick n to be fairly small or fairly frequent. But when it is smaller, you're then going to be placing more burden on your high-level policy, because it needs to be making accurate goal predictions more frequently on more states. And you'll be spending more compute as well. So both these have pros and cons. In general, if we wanted to think about kind of how these pros and cons relate to each other, we can think about how these pros and cons lead to different downstream performance. And with regard to estimating when you're done and accounting for mistakes, if you actually make a mistake in estimating when you're done, then you could actually end up in a situation where the agent is perpetually stuck. If it thinks that it's not done, but it is actually done, then it will actually just stay in that state, because the low-level policy will kind of keep on predicting this, won't actually be making any more further progress on the task. So this actually is a pretty kind of rough outcome for these kinds of errors, even if they're infrequent. And then for option 2, if you make a mistake in predicting the subtask, because you're querying the high-level policy more frequently, this also has a bad outcome, which is that the low-level policy might kind of stop making progress on the final task and might be taking the wrong actions for n steps until you get hopefully a more accurate goal prediction. And generally between these two things, these errors are more fatal. And as a result, kind of typically a lot of the hierarchical systems out there opt for choosing option 2. because of the simplicity and because some of the mistakes that the high-level policy might make when it's queried more frequently are less fatal than mistakes with regard to estimating when you're done and like what subtask, whether or not you should kind of reaccount for past goals. It's also worth mentioning that you could potentially combine these where you try to estimate progress, but then if it's been a long period of time, then you requery anyway. But yeah, the takeaway is that generally option 2 is typically what people do, where you just query at a fixed lower frequency. Cool. So let's look at some example systems. I guess one thing that I'll mention is that hierarchy is like pretty popular these days. So here are 4 systems that were all kind of announced in the last like 4 months. And they actually all use hierarchical systems. So these are all like fairly long horizon tasks where you're like cleaning a bedroom, handing over objects and kind of pouring them or putting them into bins, putting away objects into a fridge, putting fruit into bowls. And if you look at the architectures for these things, they all have some sort of higher level model that's predicting intermediate goals and some lower level model that is kind of predicting low level actions. These are in robotics domains, likewise in language model domains, things like chain of thought, where you're kind of reasoning through intermediate steps, and then actually outputting tokens for those steps is also really popular for completing more challenging language tasks. Cool. So I want to cover a few examples of these systems, and I picked examples that I think illustrate a few different design choices that are helpful and actually have comparisons on those design choices that kind of elucidate some of the benefits of one design choice versus another. So let's start with talking about hierarchical imitation learning systems. And we'll start with language subgoals. And let's first talk about like what the data would look like for training a hierarchical imitation learning system with language subgoals. So, the data, this will be kind of a real robot example, and what the data looks like is actually it's going to use data of a long horizon demonstration of completing the complete long horizon task. And so in this case, the task is to make trail mix and put the trail mix into a bag. And with this long horizon demonstration for the full task, it will then be segmented into with language labels for each segment. And in this case, the segments in the data can have a variable length. So variable, like you might kind of, if for example, the robot trajectory looks something like this, then you might have like the first subtask is like something like this. The second subtask is maybe shorter. The third subtask is maybe longer. So you'll have variable frequency in the data, but the actual system will later be using a fixed frequency where it's kind of requerying more frequently than like the typical segment length in the data. So these are different language labels. These labels could either be kind of recorded during data collection, where you're actually saying, I'm going to pick up the bag and then do a demonstration of picking up the bag, then say I'm going to pick up the metal scoop, do a demonstration of that in sequence. Or you could do it post hoc, where you just collect the full demonstration and then with a labeling interface, label like this segment is picking up the bag, this segment is picking up the metal scoop, this segment is getting M&Ms, and so forth. So we have segmented demonstrations with the associated language command. Here's another example of what this would look like, where, and this kind of shows that like one segment might be longer for picking up a slice of cheese, a different segment might be shorter for putting the cheese on the bread, and so forth. Cool. And then once we have this data, we'll train a high-level policy and a low-level policy with imitation learning. And the high-level policy will be outputting the language labels from the observations, and the low-level will be taking the language labels and the observations and predicting the actions. So what this looks like is taking an image observation, so an RGB image, passes it into a high-level policy that's trained to predict the language label. And then you'll have a low-level policy that takes the language as in addition to the observations. In this case, the work chooses to use not just RGB images, but also joint angles as input to the low-level policy. And generally it's okay to have actually this sort of mismatch between observations for the high-level and the low-level policy. And then the low-level policy outputs joint commands. And the low-level policy operates at 50 hertz. And I can't remember the exact frequency of the high-level policy, but I think it's something around 1 hertz. Cool. So that's the general setup. Now we also learned about DAgger. And you can think about if we just do imitation learning on the offline data, we might have issues where we're training these like somewhat independently, although the data is at least of the full long horizon task. And we can actually use DAgger with these systems on both the low-level policy and the high-level policy. Now, one thing that's pretty cool is that actually for the high-level policy, we can actually update the high-level policy with language supervision. And so DAgger on the high-level policy is actually in language space, not in joint space. And so in this particular approach, in principle, you can do DAgger on both low level and high level. In this particular approach, if you're to do it on the high level with freezing the low level, you would kind of be running the policy, the full system, and then you would then kind of type or speak a language command that is going to override the high level policy. And then kind of continue collecting data, and then at some point you might give control back to the high-level policy. And then from there you can fine-tune and actually do gradient steps on data that has these kinds of language interventions to actually fine-tune the high-level policy. And when you do this together with the high-level policy and the low-level policy acting as one system, then you can actually adapt the high-level policy to deficiencies in the low-level policy. So for example, if there's one language command that the low-level policy makes a mistake on, then you could actually issue some corrections to help compensate for that mistake. So yeah, I guess to summarize, we can train the high-level policy and the low-level policy both with imitation, and then freeze the low-level policy and update the high-level policy with DAgger by supervising on language corrections. And so as a video of what this looks like, these yellow commands are showing the output of the high-level policy. And then the robot motions are showing the output of the low-level policy. So at the beginning, the high-level policy is saying pick up spoon. The robot picks up the spoon, move the spoon towards me. So then it says I want some peanuts. So then the low-level policy scoops peanuts. Then the high-level policy says move the scoop into the bag. The low-level policy starts to do that. At this point, you'll actually notice that the robot's about to make a mistake. And so that's when you can intervene. And instead of telling the robot move the scoop in the bag, because it seems like the low-level policy isn't going to do that correctly, you could then intervene and say, move the scoop into the bag. Or sorry, instead of saying move the scoop into the bag, you say move the left arm to the left, go higher, move the scoop into the bag then. And so these user commands are overriding the high-level policy. And then at this point, you can give control back to the high-level policy, and then the high-level policy predicts pour into the bag and get some banana chips and so forth. So that's kind of what this sort of DAgger intervention looks like in the high-level space. And then after you fine-tune the high-level policy on those kinds of interventions, the high-level policy can then self-correct and know that the low-level policy is making a mistake, where it was about to make kind of the same sort of mistake again. And then the high-level policy says, go higher, and then move the scoop into the bag to kind of prevent that sort of mistake. And so this is an example of like the high-level and low-level policy adapting together to account for deficiencies. Cool. Now we've talked about hierarchy versus flat policies. You could ask, you can actually do a comparison, in this particular setup, does hierarchy outperform using a single flat policy to do the long horizon task? This comparison is actually from a different research paper, but it has basically the same approach. And it finds that in terms of like task progress, there's a 34% improvement from using hierarchy versus training a single policy to do the full long horizon imitation learning task. And in terms of like following instructions, there's also a gap. This is kind of this instruction accuracy metric. And you can also actually compare DAgger to imitation learning for the high level policy. And you can also see that there's like an improvement from using DAgger compared to just using vanilla imitation learning. And this is the sort of improvement that you get from adapting the policies together. Cool. And then generally with hierarchy, the nice thing about hierarchy is you can do longer horizon tasks. And so with this full system, you can, for example, get the robot to put 3 objects into a Ziploc bag, which is like traditionally a pretty difficult task to do, especially in one go. And likewise with a similar system, you can also get a robot to the high level command is clean the bedroom, and then the low level policy will output things like pick up shirt, put shirt in basket, pick up shirt, put shirt in basket, and later pick up the pillow, adjust the blanket, put the pillow at the top of the bed, adjust the pillow, pick up tissue, put the tissue in the trash can, and so forth. And so these are things that would be very hard to do if you just trained like a single flat policy. So instead of using language, we could also use images as that intermediate representation. And so what this would look like is instead of having the high level policy output language, you would output a goal image. And so it'd be like, this is the kind of an image of what I want you to accomplish in the future. In practice, you can use a generative model, like an image editing model, to do this, that takes as input the image at the current step and then edits that to look like an image at a future time step that you want the robot to achieve. And then the low level policy would no longer be language conditioned, but would rather be a goal image conditioned policy. And so you can think of this as a kind of like an inverse, like a multi-step inverse model that takes as input the current image, some future image, and then outputs the actions that you can take to get to that goal image. And then both of these will be trained again with imitation learning. And one of the things that's pretty nice is that you no longer need to segment videos with language annotations to do this. You just need the videos of the long horizon task. And to train this high level policy, you can train it on like robot data and predict like future images in the trajectory, like from 1 second or 5 seconds into the future or 10 seconds in the future. But you could also actually train this high level policy using like YouTube videos or something like that. To predict like what are future images that might accomplish some long-term goal. And so that sort of data, that sort of unlabeled video data can be helpful, especially if data from like the robot is more sparse. So then an example of what this looks like is, say the task is to move the wooden bowl to the top of the table. You pass that into the high level policy that then generates images, which are shown with the pink border. And then that generated sub-goal image with the pink border is passed as input to the low-level policy, which then predicts actions. And both of these policies, again, are trained with imitation learning on demonstration data, and potentially also, if for the high-level policy, can be trained on video data as well. So this one is putting the toothpaste in the wooden bowl. You can see that it generates these sub-goal images of, like, for example, holding the toothpaste above the bowl. It then reaches that. Then it generates a sub-goal of like lowering the arm, and so the robot lowers the arm to complete the task. And then this last example, the goal is to open the drawer. The first sub goal is to like put the gripper on the handle. Then the next sub goal is to move the gripper to the right so that it opens, and so forth. Another thing that's nice about this sort of approach is that if you don't have if your policy sees objects that it's never seen before that are hard to describe in language, then that's something that it can more easily describe in images, because it can more easily generalize across the objects that it's seeing and generate pixels for those images if it doesn't know like what the semantic name for that object is. Cool. And then for this sort of thing, you can also do a comparison on like, is it helpful to include those unlabeled videos for training the high level policy? And if you only use robot data, you get performance that looks like this. And if you add videos of humans for training the high-level policy, you get like an increase in performance compared to just using the robot data to train the policies. Now, we talked earlier about how chain of thought can replace hierarchy, and there's also approaches that have developed chain of thoughts versions of this, where you can have some high-level task and the current observation, and then actually like output either sub-goal images or subtasks. You can also have other representations like bounding boxes or waypoints, and then output the action. And there are some like recent approaches from the last like 1 year, basically, like quite recent, that do something like that. The other thing to note is that this is with imitation learning, and we'll talk about reinforcement learning in a minute, but generally for these large-scale systems, to date, for the most part, they use imitation learning more so than reinforcement learning, and fine-tuning them with reinforcement learning is in some ways an open kind of research question for like what is the best recipe for accomplishing that at large scales. And it's also a pretty important research direction, because if we think about this slide right here, the kind of performance of these systems is still not like super reliable. And these are I should mention, these are in pretty challenging situations with like held out objects, that the robot hasn't seen before. So that it's kind of out of distribution compared to what it saw during training. But if we had a way to train these with reinforcement learning, then we should be able to get these performances, to be much higher compared to using imitation learning. So the question is, like we talked about personalized recommendation systems, and could hierarchy be useful for that? Generally, I can't, like, it's not something that I've seen before, and generally when I've seen hierarchy, it's usually been for like pretty like longer horizon problems and tasks that are more complicated. In like language modeling, it's been used for like math problems essentially, and like kind of things where you need to kind of have multiple steps for completing something. Yeah, I could think about it. Yeah, so in this case, the high-level policy is an image generative model, and what it does is it's going to take as input, it's trained to take as input like an image observation and some sort of high-level goal, so like goal high level, and then you have a neural network, and that neural network is going to be trained to output OT plus K. And so it's going to be trained to generate an image of a future image. Trained to generate a future image. And you can get this as if you have videos, then you don't need language annotations to get this image. In terms of the architecture, it's using a diffusion model to generate these images. That's why you saw the noise kind of moving into the image. In the direction of the goal. Yeah, so this particular goal might be on the horizon of like, I don't know, like a minute. And this sub-goal could be in the direction, like could just be like, I don't know, 10 seconds in the future, something like that. Yeah, so in terms of using image editing models, that sort of general pre-training can be useful because it teaches the model how to generate images in general. And then the videos that are used, they're actually videos of people doing different tasks that have a single language annotation for what the person is doing in the whole video. And so those videos are like especially useful to include because they're kind of pretty relevant. If instead you included like random videos on YouTube, it's a little bit harder, but it might still teach it about like if there's some like future thing, what are images that could happen in the future, and that is useful pre-training for this kind of task. Yeah, so you're asking like, what if the language isn't accurate, and what if this is like a sketch instead of like a real image? So good question. I guess first, if you wanted to use sketches here, you would just want to ideally like train the low-level policy to be able to use that sort of thing. And there are actually approaches that have like taken images and you can kind of convert them into a sketch and train a low-level policy to do that. And you don't actually necessarily need this to be a full image. These are just kind of, I should mention, two example representations. And language is actually particularly popular as an intermediate representation. But there's lots of other representations you could use, including sketches, including like, I don't know, like a trace of where you want the robot to go or something like that. And then in cases where the language isn't accurate, if it is describing something that's like different, then oftentimes the robot will then follow that different task until it's been told to do something different. And so that if the high-level policy is predicting language that is bad, then the system will suffer. There are some cases where the low-level policy might also ignore the high-level policy, and still, like if you'd kind of give it gibberish, it might just kind of have some sort of, in some ways, like kind of default behavior, because it was trained to output actions, and it often like will, like for like different states, for example, if it's like holding the pasta right here, then even regardless of any sort of language input, chances are the next action is actually to pour it. And so if you don't give it a language instruction, or if you give it a noisy language instruction, it might still continue to pour it just because it knows that for that state, typically that's what you do next. Now let's talk briefly about hierarchical reinforcement learning. So when I was bringing up examples of this, I think that the hierarchical imitation learning systems are like quite recent, and I don't have too many, I think, exciting examples, or examples that I was excited about with regard to hierarchical reinforcement learning. But there are a few example systems that you can look at, and I think that generally getting these kinds of systems to work really well, like potentially on top of the initialized hierarchical imitation learning systems, is something that's I think really exciting and important to explore. But generally, in terms of like what has been done and what exists, you can do hierarchical reinforcement learning with trying to reach different states. And this could be the relative target position of some agents or some objects. And kind of one cool work that does this is it has this like four-legged ant agent that you might have worked with in homework 1. And its goal is to get over here. And to get over there, it actually needs to push this object to the right and then move there as a result. And then there's also this example where it needs to get over here. If it tries to go directly there, it will fall in this crevasse. And instead, it needs to push and make a little bridge for itself and then walk over here. And these are pretty long horizon problems where if you just try to take actions greedily, you won't be able to get to the goal. And so the work trained a goal condition policy conditioned on goal states with a reward of reaching those goal states. And then it trained a high-level policy to output goal states. And those kind of goal states are the high-level actions. It actually also used hindsight relabeling for the high-level policy to kind of actually relabel high-level actions, or to relabel the goals that the high-level policy should output in certain circumstances. And it used an off-policy algorithm to train this in order to allow it to work effectively. And then another work that does hierarchical reinforcement learning uses language goals. So you could do goal states. You could also do language goals. This trains a language condition policy. It uses language relabeling. So instead of goal relabeling, it does hindsight relabeling in language space. And then the high-level policy is trained to output language, which is actually a pretty difficult task. And it again, this is a work that's not too recent, and so it's from like 2019, and so the tasks are relatively simple, where it's trying to be able to arrange these different objects in particular order, where you need to like push the green object, push the red object, the blue object, and so forth. Cool. And then the last thing that I'll mention is that we've talked about these scenarios where you're supervising the low-level policy to like reach some goals, and the high-level policy to output those goals. Now, there's in some ways like a really cool research direction of, instead of actually supervising it to do certain goals, can you actually discover discover subtasks or discover skills that might be useful without requiring supervision on those low-level skills? And here's one example of a work that studies that, where it, in this kind of simple half cheetah agent that you might have also seen in one of your homeworks, it's able to learn skills like backing up, walking forward, doing, I think a front flip, and so forth. And then in principle, if you discovered skills without supervision, then you could try to sequence those together to do harder tasks. But this is generally still an active research area and something that's pretty challenging to scale up, especially in very large state spaces. Cool. That's it. And next time we'll be talking about reinforcement learning for robotics, specifically learning with autonomy, and a guest lecture from Ashish Kumar on the Tesla Optimus team.